Greetings. So welcome to today's session. So let's continue from where we stopped in the previous class. So if you recall, like we were dealing with this linear dynamic bicycle model. And then like in the previous class, we rewrote the governing equations in terms of the yaw rate and the side slip angle. I request everyone to mute themselves. So we rewrote in terms of side slip and yaw rate, and then we found that the governing equations became two first order ODEs in the side slip angle beta and the yaw rate R. Then what we did was that see, now I hope the connection or the reason why we studied all that fundamental theories of dynamic systems would be clear to us, right? Because we studied a lot about dynamical systems theory, transfer function, state space, and so on, right? So this is where everything comes together, right? So we saw that, if I were to analyze the stability of the cornering motion, I need to essentially evaluate the eigenvalues of the state matrix here. And that's what we did, right? So we just did that. And then for stability, as we know, we require all the eigenvalues to be in the left of complex plane. And then we use simple ideas. Since we got a second order characteristic polynomial, all the three coefficients must be non-zero on the same sign. Since the coefficients of lambda squared and lambda were already positive, so the constant term should be greater than 0 for stability. So essentially that's what we used, and we got this condition, right? Finally, it just boiled down to this condition, right? So this is what, this is where we stop, right? Okay. So let's continue from here. So in fact, by looking at this condition, we can immediately see that anyway, we need L plus KB times Vx squared by G to be greater than 0. L is anyway positive. Vx squared by G is also positive, right? So everything depends on the sign of KB, right? So as far as satisfying this constraint is concerned, right? So one can immediately observe that when KB as a parameter is greater than 0, okay, we can immediately observe that stability condition, right? The above stability condition is satisfied for all Vx. So I'm sure all of us agree to that point, right? So when KB is positive, anyway L is positive. See, if you look at it, L is anyway positive, right? Vx squared by G is also positive, right? So in this expression. So everything depends on the sign of KB. So if KB is positive, KB times Vx squared by G is certainly positive. L is positive. So we are adding two positive numbers. The sum is certainly going to be positive, right? So essentially, we are going to ensure stability for all speeds, right? So this condition is what is called as an understeer condition, okay? So when the cornering, when the understeer gradient, right, or the understeer coefficient of the vehicle is greater than 0, we have stability for all speeds. And consequently, we say that the vehicle is in a state of understeer, okay? The good thing is that we ensure stability for all values of Vx. What is the trade-off? We will look at that as we go along, okay? So we will see that there is a trade-off in terms of performance, right? So nothing comes free. So we will see what happens with understeer vehicles as we go along. If KB is exactly equal to 0, okay? So once again, if KB is exactly equal to 0, the above condition becomes L is greater than 0, which is anyway true, right? So the wheelbase is always going to be greater than 0. So once again, stability condition is satisfied for all Vx, right? So that's once again something we can immediately easily figure out or easily conclude, right, from this above expression. Okay, so this condition, when KV is exactly equal to 0, corresponds to the vehicle being in a state of neutral steer. So in neutral steer, the load distribution and the cornering stiffness of the tires, right, are such that the understeer gradient or the understeer coefficient, which is this WF by 2C alpha F minus WR by 2CR, is exactly 0. Okay, so essentially that is what is called as a neutrally steered vehicle, or the vehicle is said to be in a state of neutral steer, okay, under this condition. Now, the interesting case comes about when kV is less than 0. When kV is less than 0, things become a little bit interesting, okay? So let us now figure out what happens, okay, when kV is less than 0. So let us essentially take kV as minus the absolute value of kV. Okay, so I'm just representing it like this. Why? Because let's say kV is minus 10 power minus 3, right? The absolute value of minus 10 power minus 3 is 10 power minus 3, right? And we are putting a negative sign. This is just for our notational simplicity. Okay. Now we can observe that when kV, this condition, becomes negative, there may arise some scenarios when this inequality will be violated, right? Because we need L plus kV Vx squared by G to be positive, right, for stability. Now, when kV is less than 0, there may arise a scenario where this inequality may be violated. So let's figure out what is that limiting condition. So the limiting condition or the limiting speed. Okay, so let me rewrite this. Okay, we can essentially call it as limiting condition, right? Limiting condition in this case, okay, can be written as, say, what do I mean by limiting condition? See, initially to begin with, let's say this left-hand side of the inequality is positive, right? At some point, let's say it has to become 0 to go to negative, right? So that's what we are going to call as limiting condition. So the limiting condition is going to be L plus KV Vx squared by G should be equal to 0, right? So let's analyze this further. So what we are going to do is like this. I'm going to write as L minus magnitude of KV Vx squared by G. Okay, so we have just substituted for KV as negative of magnitude of KV. Okay, so if we substitute this and then like we essentially rearrange the term, we get Vx squared as Lg divided by magnitude of KV. Okay, so this essentially gives us an expression for what we call as a critical speed. It is nothing but square root of Lg divided by magnitude of KV. This is the speed beyond which stability is lost. Okay, so this is what is called as critical speed. Okay, so what is this critical speed? This is the speed beyond which stability of the vehicle is lost when kV is negative. Okay, so this is what is called as critical speed. And this condition where kV is less than 0 is what is called as an oversteer condition. Okay, so when kV is less than 0, the vehicle is said to be in a state of oversteer. Okay, and there is this corresponding critical speed, okay, beyond which cornering stability is lost. Okay, so when kV is less than 0, okay, cornering stability is lost. For Vx greater than Xc. Okay, so if longitudinal speed becomes greater than the cornering, the critical speed as derived here, which is square root of Lg by magnitude of kV, cornering stability is lost. So that is the trade-off with oversteer. Okay, we will see that with oversteer, we will get faster steering performance and maybe better. What to say? Some steering characteristics are going to be better, as we will analyze shortly, using our perspective from dynamic systems theory. However, there is a price to pay, right? So cornering stability may be lost beyond a certain speed, right? So this is why we see that. See, for example, if we take some, let's say, even motor race cars, right, which may be oversteered, right? Sometimes cornering stability may be lost, right, at some speeds and also at some conditions, operating conditions. Please note that KV is dependent on not only the load distribution, but also the cornering stiffness of the tire, right? The cornering stiffness of the tire is also a varying parameter, right? So that should be kept in mind, right? So when we are doing the analysis. Okay. So any questions about this analysis? And how we have brought in this concept of understeer, neutral steer, and oversteer, okay, using this dynamic systems analysis with the bicycle model, the linear bicycle model. So any questions on how we have used stability theory to derive these expressions and concepts?
Sir, one question from my side is, in this condition, we are not bringing the road conditions into the equation, right, sir? Like, say, the angle of the road or a track to surface or something.
Okay, so what about road conditions, right? So please note that road conditions also will be affected in the will influence the lateral force generation characteristics, right? And consequently will affect the values of C alpha F and C alpha, right? They are not constants, right? Is it not? Depending on the road conditions, the initial slope of the Fi alpha curve is also going to change. Correct? Yeah. That's how they will come into picture.
Sir, can you please scroll up and show like this KV, like any reason why we have took modulus of KV?
Why, which step are you talking about? The oversteer? No.
Yes, sir, for oversteer, like it's.
So we could have kept it like that. In some textbooks, they will essentially go from here and then like write Vx critical as square root of Lg by minus Kv. Yeah, I just wanted to avoid minus Kv within a square root. Okay, that's all. It's just a matter of notation. Okay. So if one puts minus Kv within a square root, right, one may get the idea that, oh, this is going to become a complex variable, right? Not necessarily. I hope now the reason why I chose this notation is clear, right? Okay.
Yes, sir.
So see, this is nothing but like this, like as an example, let us say we want to write minus 10, right? What am I saying? I'm just writing minus 10 as minus of the absolute value of minus 10, which is anyway minus 10, right? So okay, we'll get the same answer, right? Which is minus. Yeah, that's all I do. Okay. Any other questions? Okay, so before we look at the performance, see, I only looked at from the perspective of stability, right? And introduced this notion of understeer, neutral steer, and oversteer. Before we go to performance of all these conditions, like I also wanted to present analysis from a different perspective, which is what you will find in most vehicle dynamics textbooks. Okay, so I just wanted to share with you that we have done a slightly generic analysis, which can be even used for cornering dynamics and control and other applications. But if you take a look at many classical vehicle dynamics textbooks, they will essentially deal with what is called steady state cornering to derive a similar same expression for the understeer gradient and then motivate understeer, oversteer, and neutral steer. But then the reason I did it this way is because I wanted to convey to you that the notions hold even under dynamic operating conditions, not only under steady state operating conditions. So now I hope it's clear to all of us why we took some time at the beginning of the course once again to study transient response, steady state response, and so on, right? See, if we look at steady state response, like we essentially that corresponds to region once the transient effects of an input or an initial condition die down, right? So that is what we call a steady state response. So steady state cornering, what is the idea? Let's say we are going straight, we give a steering input, there is going to be some change in the heading, but then after some time, like if things are nice, my car is going to go on a go steadily on a arc of constant radius, right? Once it reaches that state, I am at steady state. The previous model which we studied, right, the dynamic bicycle model can be used even during the transient state, That is why I'm calling that approach as a more generic approach, right? Is something which I would prefer. However, I should also introduce the steady state model, which is found in most textbooks, to show you the differences and also drive home a few important points. Okay, so that is why I'm going to do this analysis. So I hope the context of this discussion is clear. So what is done in steady state cornering? Once again, we assume Vx is constant. Okay, we assume that, we assume that Vx is constant. Anyway, that assumption was done even before, right? When we wanted to do the linear bicycle model analysis. Okay, that's fine. But more importantly, we assume that R is constant. Okay, this is the more important assumption. Okay, we assume that the radius of turn is constant. So this means that, let's say, as I mentioned, let's say our vehicle is going straight. I give a steering angle input, and then it reaches a steady state. Okay, it goes in a steady turn of constant radius, and then we are looking at what is happening. Okay, so you can immediately see the scope of this model. Okay, please remember that, right? So this implies that the yaw rate also has reached a constant value, whereas yaw rate was not constant previously. Okay, yaw rate, which is psi dot, which is R, becomes equal to Vx by R, which is also a constant. Why? Because Vx is constant, R is also constant. So the ratio of the two should be a constant, right? So please note that point. Okay, this is where one important difference comes in. Okay, between the previous model and this model. In the previous model, if you recall, we consider R to be a function of time. Okay, there was an R dot term. R dot was not zero, right? We could have an evolution equation for R dot. The yaw rate R was a state variable, and there was an evolution equation for R dot. However, in this model, like we see that R is a constant, okay, which is Vx by R, and R dot is zero. Okay, so I hope this definition, this scope of this model becomes very, very clear. Okay, so now let me explain what this model is, and then like we will derive the corresponding equations. Okay, so this is just a simple schematic which shows the various variables associated with this steady state cornering model. So let me once again explain what the relevant parameters are. I'm sure by now all of us are familiar with these, right? So essentially we once again approximate the vehicle by the line segment AB. We are once again considering the bicycle model, okay? And let's say the center of gravity is at the point C. So essentially capital L is the wheelbase, and C is the center of gravity. And at this point, we have a local frame of reference, small x, small y, okay? And we also have a global frame of reference, capital X, capital Y, right? So even capital X, capital Y is the global frame of reference, right? So these are things which we already are aware of, right? And let us say that, like we give a steering angle input of delta to the front wheel, okay? The rear wheel is not steered. And alpha F and alpha R are the slip angles at the front and the rear wheel. So steady state cornering doesn't mean that we are neglecting the forces and the slip, okay? We are considering the slip angle and the slip angles of the front and the rear wheels, okay? And V is the velocity vector at the center of gravity, and Vx is the longitudinal speed, and y dot is the lateral speed at the center of gravity. This R is the turning radius, okay? And we are going to make a very important assumption. We assume that the turning radius is much greater than L. Okay, so we assume this is also another important assumption. We didn't make this assumption before, right? So we can see that there are many assumptions which are stacking up. Like when we learn this so-called steady-state cornering model, right, as presented in many textbooks. So it's important for us to learn this. Okay, that's why I'm teaching you this. And let us say the point of intersection of these line segments is the instantaneous center of turn, okay, which we represent by the point O. So this is the instantaneous center of turn, okay, and the length of the line segment from O to C, okay, is the turning radius, right? So we are familiar with all this notation by now. Okay, so this is the instantaneous center of turn. Okay. So FIF and FIR are going to be the lateral forces at the front and the rear tire rod interfaces respectively. Once again, we will take FIF and FIR to be directly proportional to the slip angles. So that's an assumption we will stick with. Okay, we will take FIF to be 2C alpha F alpha F and FIR to be 2C alpha R alpha. Okay, so those are assumptions which we will continue to make. Okay, so these are the main variables involved here. So let's do some simple analysis. Okay, so if I were to look at this angle immediately we can observe that this is going to be delta minus alpha F. Okay, the small angle which the velocity vector of the front wheel makes with the longitudinal direction is going to be delta minus alpha F. This angle between this dotted line and the velocity vector of the front wheel is a right angle. Okay, so that's something which all of us know. So consequently, this angle, which is angle OAC, is going to be coming out like this. How do we get this, right? It's going to be 180 degree using the fact that for a straight line, the sum of the angles made by the constituents is 180 degree. So I will get 180 degree minus 90 degree, which is this angle, okay, minus delta minus alpha, right? Or plus delta minus alpha, right? So this is sorry, delta minus alpha. Yeah, delta minus alpha, right? So this is what I get. So this is turning out to be 90 minus delta plus alpha. Okay, this is angle OAC. All right. Okay. So I hope it is clear how we got this. And this angle, sorry about that. This angle OCA is a right angle. Okay, so this is going to be a right angle. Okay, so consequently, how do I get this delta minus alpha F here? It's once again by looking at the triangle OAC, the sum of the three angles should be 180. So this time we are getting it by 180 degrees minus 90 degrees, which is the angle OCA, and the angle OAC we just calculated, right? It's going to be 90 minus delta plus alpha F. So consequently, we get this as delta minus alpha F, right? I hope it's clear how we got the angle AOC as delta minus alpha. All right, okay. So we are going to use the same logic for the other triangle also. So we can immediately observe that this angle is also 90 degrees. Okay, this angle is alpha R. So this angle is going to be equal to 90 minus alpha R, right? So because the other bigger angle is going to be 90 degrees, right? And consequently, what we will have this angle, okay, which is alpha R, that is, that is going to come out to be what? Okay, once again, looking at the triangle OBC, it's going to be 180 degrees minus 90 plus 90 minus alpha R, okay, which in turn is going to be alpha R. Okay, so that's what we have. All right, so I hope it's clear how we got alpha R, right? So we have derived expressions for angles AOC and angles BOC. So immediately we can see that angle AOB, okay, angle AOB is going to be delta minus alpha F plus alpha R. And under small angle assumption where R is very much greater than L. Okay, please, this figure is not to scale. Think that, like point number O, the instantaneous center is very far away. Let's say the wheelbase of the vehicle is, let's say 3 meters, right? And let us say, the value of R is 100 meters, right? So R is going to be much, much higher than L, right? Under that condition, this angle AOB can be approximated as L by R. Okay, so L by R is going to be pretty small. So this is an approximation we can once again do. So once again, please note that this derivation has a lot of assumptions. Okay, that is what I want to reiterate again and again. Whereas the previous derivation, which was long-winded, but was more generic, had fewer assumptions. Okay, so here we assume that R is constant, point number one. We also assume that R is much greater than L. Consequently, the small angle assumption became true in addition to other small angle assumptions. Okay, so that is also another restriction we have. So this leads to this very famous equation, which you will find in many textbooks, that delta is equal to L by R plus alpha F minus alpha R. Okay, so this is a very prominent equation that you will find under lateral dynamics or cornering dynamics in many textbooks on vehicle dynamics. Okay, so however, through today's discussion, we have figured out, like under what conditions this is true. Okay, so this equation, of course, is true when the units of all angles are in radians. By and large, what happens is that, like, we may use degrees also. When we use degrees, we will see that this equation is written as 57.3 L by R. Delta equals 57.3 L by R plus alpha minus alpha R. Okay, now delta, alpha F and alpha R are in degrees. And how did we get this 57.3? It is just 180 by pi. Okay, please note that 180 degrees is going to be pi radians. So I want to convert L by R from radians to degrees. So we multiply 180 by pi, and 180 by pi is 57.3. Okay, so this is the corresponding other form of this equation that you will find in most textbooks when the angle measures are essentially given in degrees. Okay, so however, like, please note that, like, there are a lot of assumptions, more assumptions than before to get these equations. Okay, so I hope that is clear. All right, so this, yeah, please go ahead.
Sorry, sir, one question. In this front wheel, sir, this V, that V is the heading direction of the front wheel, right, sir?
Okay, so let me draw that separately here. Okay, so V, what is V? Okay, so let's say this is the front wheel. Okay, I'm just drawing an exaggerated diagram just to show the things. Okay, so let us say this is the center of the front wheel, and let's say this was the longitudinal axis. Okay, so this angle is delta. Okay, on the other hand, the velocity vector of the front wheel is at some angle. Okay, it is not along the central wheel plane. So there are multiple things at stake here, right? So this solid blue line indicates the central wheel plane orientation of the front wheel, whereas the pink line is the longitudinal axis of the vehicle. All right, whereas this
Red one.
angle, right, the red one shows the local velocity vector, and consequently this is the slip vector. Okay, so slip angle. That is, slip angle is the angle made by the local velocity vector with the central wheel plane. And what is the heading of the vehicle? Heading of the vehicle is this angle. Okay, let's say this is the global x-axis. The angle between the pink line and the global x-axis. I hope now things are clear, right?
Yeah,
Okay.
sir. But this VF, the FYF is at perpendicular to VF, right, sir?
Okay. So if you recall FYF, you are right. It is perpendicular, in fact, to the longitudinal axis. Okay. But then, to VF, sorry, right? But then
Okay.
if you recall a couple of, when we started off with this derivation, let me go up, okay, and reiterate this point since this question has come up. Okay, so one minute, just give me a second. Go up all the way. Yeah, if you recall, okay, this actually, this FIF should be perpendicular to the central plane of the beam. Okay, now we are essentially taking it perpendicular to the what to say, the longitudinal axis, right? In all the derivations. So the component should be strictly FIF cos delta. That's where small angle assumption comes in. Okay, you are right. This model, see, it's very important for us to note. If I want to essentially analyze small radius of turn, radius of curvature turns, ROC turns, right? This model, I have to be very careful in applying. All right. I hope this clarifies the point, right?
Yes, sir. Understood.
Yes.
Like
So this is once again an approximation. Okay, so see, we have done the small angle assumption at the beginning. Okay, so that is why I went through the assumption step by step, because so that we understand all the assumptions very carefully, right? Because to me, these are very important, right? We should know when to utilize these models, and more importantly, when not to use them. Okay, so tomorrow, let us say someone gives me a problem of analyzing a low ROC term, right? I would be very careful before using this model, right? Yeah. Okay, so I would draw a,
Okay.
Yeah, I would draw a new free body diagram and derive the equations once again, right?
Sir, here this dx is constant, but y is also constant, is it?
Y is not a constant, right? Y will be changing. You mean y dot, is it? The y component of the velocity vector.
Y component of the velocity, yes, sir.
So we will come there. Okay, so essentially the y component of the velocity vector, you know, like if you look at it, y dot will be essentially what to say, constant, right? Because we are going with a steady state turn. However, the lateral acceleration will have the centripetal acceleration term, vx squared by r. See, previously we had that vy dot plus vx psi dot, right? If you remember. So I think good question. Let's go ahead and clarify these. Okay, so these are all very important questions. Okay, so let us go back. That's why I'm going back to this derivation. Okay, this derivation is more generic, okay, than the previous derivation. So where was this? So you see here, right? So ay was, I'm suppressing time. Okay, it was y double dot plus vx psi dot. Okay, in general, right? So in the dynamic model, in this current model at steady state, okay, the steady state model that we are currently doing, what are we doing? We are essentially taking y dot to be constant, psi dot to be also constant, which is vx by r. So consequently, the lateral acceleration under steady state just become vx squared by. Okay, so I hope this explains why even when we have steady state motion, let's say we attach a string to a ball and we keep on turning in a circle at steady state, right? We call the centripetal acceleration as either r omega squared or v squared by r, right? I hope this explains it. Okay.
Y double dot is 0.
Y double dot is 0. Y dot becomes constant, right? Y dot is constant. Correct?
Yes.
I hope this explains your question, right, sir?
Yes, sir.
Thank you. And I hope that now it becomes clear why I am stressing that this model which I'm showing right now is more generic than the specific model that we are dealing with. But why am I teaching you that model? Because that's what you will find in many vehicle dynamics textbooks. But then we need to be aware of, it is useful, but then we need to aware of the context in which it can be used. Okay, I hope my point is clear, right? All right, okay, we come here. So yeah, so we derived an expression for this delta, and then now we move on. Okay, so we are now going to write down the equations of motion for steady state turn. So for translational motion, for translational motion along the lateral direction. So as we know, Fy, if we add the lateral forces, they should sum to m times Ay. Okay, so that's what we have. And we just saw that the lateral acceleration in steady state is v squared by r, right? So essentially we have Fyf plus Fyr is equal to m times Vx squared by r. Okay, that's what we have. Okay, I hope this is clear to all of us. Now, for what happens for rotation, once again, I times psi double dot should be equal to the torque. However, as we saw, psi dot is a constant, right? So consequently, what will happen here, right? So for rotation, what will happen is that the net torque is FIF minus FIR. That will be equal to I times psi double dot, but psi double dot is 0. Okay, that is why we are essentially getting this equation. Okay, is equal to 0. I hope it becomes clear as to how we are essentially having these two equations. Okay, so you remember we called these equations as T and R, right? So you can see that the equations T and R have become extremely simplified. Okay, so once again, let me go up and then show you those equations. We just saw them. If you recall, wrote these two equations as the linear dynamic bicycle model, right? Sorry, yeah. So, and then like the first one was for translation, second one was for rotation. Under steady state model, y double dot is 0, psi dot is Vx by r, psi double dot is 0. So that's why these equations got simplified, right? And we have written them down the way we have written here, right? So that's what happens to these two equations. So consequently, from this equation, we can have Fyr to be equal to Fyf times Lf by Lr. Okay, so this is what happens here. Then what we do is that like we take this equation and then like we substitute here. Okay, so this is what we are going to do. So consequently, what will happen? I will have Fyf plus Fyf times Lf by Lr. That's going to be equal to m times Vx squared by r. Okay, this is what we have. So if we simplify this equation, once again, some algebra here, but I'm sure we can immediately understand what's happening. If we take the LCM, I will get Lr plus Lf divided by Lr. That's going to be equal to m Vx squared by r. Okay, and if we simplify this further, we will get Fyf is equal to, what is Lf plus Lr? Lf plus Lr is going to be equal to L, right? This is the wheelbase capital L, right? So consequently, I will get Fyf, if we simplify this equation, I will get it as m Lr Vx square divided by L times R. Okay, so this is what we have, right? So I'm sure all of us can understand this. So this we are going to slightly rewrite in a certain way. We'll write this as Fyf is going to be equal to m times Lr divided by capital L, okay, and Vx squared by R. Okay, that's what we do. And what is this m Lr by L? Do you remember what is m Lr by L?
So weight distribution.
Very good. Okay, so you can, if you recall, m Lr by L will be the mass of the vehicle on the front wheels, right? Supported on the front wheel. m Lf by L will be the mass of the vehicle supported on the rear wheel. Okay, so please remember that. So this is nothing but, let me call it as m subscript f. Okay, m subscript f is the mass of the vehicle supported on the front wheel. So Fyf will become m subscript f Vx squared by r. Okay, this we can write as m f G Vx squared by Rg. Okay, and what is mg? It will be the weight. Okay, so I write it as Wf Vx squared by R. Okay, I hope it is clear how we got this, right? So I hope these steps are okay, right? So, and then it's clear how we got this, right? So what I did here, I just multiplied and divided by g, the acceleration due to gravity, and Wf is equal to mf times g. Okay, so that is what we will have. So now we can similarly get an expression for FIR. What will be FIR? FIR is now FIF times LF by LR, and this we are going to get it as m times LR divided by L Px squared by R. Okay, this is FIF times LF by LR. Okay, so what is going to happen? LR and LR will cancel off here. Okay, we will cancel off LR and LR. So we are essentially going to be left with M LF divided by L, Vx squared by R. And as we know, M LF by L is going to be M subscript R. Okay, Vx squared by R. Okay, and if we simplify it further, FIR can be written as M subscript RG. I multiply and divide by the acceleration due to gravity. I will get this expression. Okay, this is nothing but WR X squared divided by R. Okay, so I hope all these steps are clear. Okay, how we got this. So this is M subscript R, and M subscript R times G is W times. Okay, so pretty straightforward, right? So how we got this. Okay, so we have got expressions for FIF and FIR. Now what? Okay, so now we go and apply our small slip angles, right? Recall that for small slip angles, what do we have? We have FIF to be equal to 2C alpha F times alpha F, and FIR to be equal to 2C alpha times alpha R. Okay, so we use this to our advantage. So now what is FIF? FIF, we just got it as, WF Vx squared by Rg, right? That's going to be equal to 2C alpha F times alpha F. So this will immediately give me an expression for alpha F, right? Alpha F will be WF divided by 2C alpha F multiplying Vx squared by Rg, right? I am sure all of us understand this, right? So this we have got an expression for W. Similarly, we can get an expression for WR, right? What do you think will be WR? If we substitute for FIR, we substitute FIR equals WR Vx squared by G, right? So we already have this expression, and we will immediately get alpha R to be WR divided by 2C alpha R Vx squared divided by Rg. Okay, so we have got expressions for alpha F and alpha R. Now we go back and substitute, and we will complete our discussion. Okay, so substitute for alpha F and alpha R in the equation delta equal to L by R plus alpha F minus alpha R. Okay, so substituted there, we will get delta be equal to L by R plus alpha F minus alpha R, which is going to be equal to L by R plus WF. We can just substitute for alpha F and alpha R. We'll get WF by divided by 2C alpha minus WR divided by 2C r times Vx squared by Rg. Okay, so this is what, and this term, okay, is the understeer gradient. You know, like you can see that we get the same expression, right? So this is how we can essentially get the definition of an understeer gradient even from the steady state coloring model. And this is a very popular expression which is used, wherein delta is equal to L by R plus KV times Vx squared divided by Rg. Okay, so this is a very popular expression. Okay, using the steady state model. So what does this equation give us? For a given vehicle undergoing a steady state turn at a constant speed Vx and a constant radius of turn R, right? What is the steering angle that should be given? And immediately we can see that the steering angle, right, is also dependent on this parameter Kv, right? And in the next class, we will start analyzing these dependencies. Okay, so this is a very, what is a popular equation in cornering dynamics, which is used to evaluate the response of understeer, neutral steer, and oversteer vehicles. All right, or I should be very careful to analyze the response of vehicles in a state of understeer, neutral steer, and oversteer. Okay, so but however, please note that this expression was obtained under so many assumptions, right? So that is something we need to be very clear about. Okay, although it is widely used, we need to be very clear about the assumptions made to derive this expression. Okay, so this is an important expression. So we will utilize this expression to analyze the response of vehicles, right, under various conditions of understeer, neutral steer, and oversteer in the next class. Okay, so that is what we are going to do. Fine. Okay. So let me stop the class here today. You know, like any questions on the content that we have learned today?
Sir, not about today's, but on like the previous lecture, sir, we discussed the governing equation for the second order ODE for the dynamic bicycle model. So, like, why do we call it linear?
Why do we call it linear? Okay, good point. Let me go on. So let me go to this governing equation. Yeah, so let's go here, right? So we call this as the linear dynamic bicycle model, right? Why did we call it linear? Because the moment Vx is constant, you can see that these equations are linear in y double dot, psi dot, FIF, FIR, psi double, and all those are the terms which are dependent on time, right? Correct? So that's why I wrote parenthesis T very carefully, okay? And after that, after some time, I suppress parenthesis T, okay? So here, if you look at both these equations, the time varying variables are y double dot, psi dot of t, FIF, FIR, and psi double dot, right? So you can see that they appear in a linear fashion in this in these equations. Okay, so that's why it's a linear bicycle model. On the other hand, if Vx were a function of time, previously, if you recall, we would have got Vx as a function of time, right? So this equation, in fact, can be written as, I'm just writing on the side, if I take the second equation and put parenthesis t, this will be m times y double dot plus psi dot of t, Vx of t will be equal to the net lateral force. Now you can immediately observe this term, right? This is a product of two functions of time, right? It becomes nonlinear. Okay, on the other hand, when Vx is constant, it becomes a constant times psi dot. Okay, so it becomes a linear function. I hope that clarifies the question. Okay. Yeah.
Yes, sir. Thank you.
All right. Any other questions? Okay. So if not, let me stop the recording here.